Hello, this is AP Physics C, Mechanics, Practice FRQ Set 7, Question 2. A solid cylinder with mass m and r rolls without slipping down the inclined plane. The cylinder starts from a height of h, and the inclined plane makes an angle theta with the horizontal. Express all solutions in terms of m, r, h, theta, and g. So, solid cylinder means moment of inertia is 1/2 mr squared. Okay. This is a good thing to know. Part A. Determine the translational speed of the cylinder when it reaches the bottom of the inclined plane. Okay, so we can use conservation of energy for this. Potential energy equals K kinetic energy. And since the cylinder is rolling without slipping, there is K linear as it goes down the incline and K rotational as it rolls. Okay, so potential energy is mass times gravity times the height, which is h, equals, this is 1/2 mvf squared plus 1/2 over inertia omega squared. So we can leave this alone for now, this one too. As we find out, expand this. So 1/2 molar inertia, as I said before, is 1/2 mr squared. And we can convert angular velocity into linear velocity. So v equals r omega, which means omega equals v over r. And we'll just plug that right in here. V over r squared. Okay, now we can start canceling things out. All three of these have an m. And this square will be distributed into v squared and r squared. Which means we can cross out these two r squareds, and we're left with gh equals 1/2 vf squared plus 1/2 times 1/2 is 1/4 vf squared. Okay, combine like terms. This will be 3 vf squared over 4, and then we can divide 3 over 4 to the other side to get 4gh over 3 equals vf squared. Then we can square root to get vf equals square root of 4gh over 3. Part B. Draw the force body diagram on the cylinder as it rolls down the inclined plane. Your arrow should begin at the point of application of each force. Okay, so here's an incline and here's a cylinder, and the center will be right here, center of mass. Okay, so F of G, force of gravity, affects the center of mass, and their components of F of G. Fgx, the x component, moves the ball down the incline, and Fgy pushes it into the incline. And there's also F of n because it is touching the surface, so F of n is going against the surface, and it will be equal to Fgy. And there will also be a force of friction, F of k, at the bottom of the cylinder because that is where it contacts, and F of k pushes the bottom so that the cylinder rolls. Okay, those are all the forces, the force body diagram. Now, part C, derive an expression for the acceleration of the center of mass. Okay, so we can use Newton's second law, delta F net force equals ma, mass times acceleration. So if you look at the linear system, there are two forces causing the cylinder to move up or down the incline, Fgx moving it down, and F of k slowing the cylinder down by pushing it up. So Fgx getting opposed by F of k equals ma. So we know what Fgx is, mg sine theta. We don't know what F of k is, equals ma. How do we find F of k? We can use the rotational Newton's second law. Net torque equals moment of inertia times alpha. So this will be equal to net force times moment of arm equals 1/2 mr squared. That's our I. And our alpha can be converted to A over R, the same way we converted angular velocity into V over R. So we can cross out this extra r squared and r here. Sorry, it's not associate uppercase, okay? And we can take out R from both sides, so that's with net force equals 1/2 ma. And the only force causing the ball, the cylinder to roll is F of k. And we can plug this right into here. So mg sine theta minus 1/2 ma equals ma. We can cross out all the masses, and we can move 1/2 a to this side. So we left with g sine theta equals 3a over 2, which leaves us with a equals 2g sine theta over 3. 3. Okay, I'll make this 3 look better. 3. Okay, that's part C. Now, part D. Part D asks, what percentage of the total initial energy is in the form of translational at the bottom of the ramp? So like before, we can use PE equals KE linear plus KE rotational. So the total initial energy is the PE. I'll just call it TEI, total energy initial, equals 1/2 mvf squared plus 1/2 I omega squared. So TEI equals 1/2 mvf squared. In part A, I already expanded this, and this became 1/4 mvf squared, which means total energy initial equals 3 mvf squared over 4. So to find a percentage of total initial energy that is the form of translational, translational energy is KE linear, and we'll divide it by total energy in order to find a percentage. KE linear is 1/2 mvf squared, and total energy initial is 3/4 mvf squared. So we can cross out mvf squared, and we're left with 1/2 over 3/4, which is equal to 4 over 6, or 2/3. As a percentage, that will be around 66.67% of TEI turns to KE linear. Something like that. Now, part E. Derive an expression for the minimum coefficient of friction between the cylinder and the inclined plane that is required for the cylinder to roll without slipping. So we will use the same Newton's second law, F equals ma. Two forces affecting the linear movement of the cylinder is Fgx minus F of k equals ma. So since we're looking for the coefficient of friction, we can expand F of k. So this will be mg sine theta, and F of k is mu Fn equals m, and a, as we found in part C, is 2g sine theta over 3. 2g sine theta over 3. And mg sine theta, we can expand Fn into mg cosine theta, because f of n is equal to fgy, which is equal to mg cosine theta, equals m2g sine theta over g. So all these have mg in common. You see mg, mg, and mg. Oh, this is 3. So that's with sine minus mu cosine equals 2 sine over 3. We can subtract this to sine to get sine over 3, and add this to the other side to get equals mu cosine. And we can divide cosine to get mu equals sine over 3 cosine, or tangent over 3. Tangent. Okay, that's part E. Now part F says the coefficient of friction is now made less than the value determined in part D. So the cylinder both rotates and slips. So part 1, indicate whether the translational speed of the cylinder at the bottom of the inclined plane is greater than less than or equal to the translational speed calculated in part A. Okay, so when there's less friction, that means there is less force causing the cylinder to roll, which means there's less kinetic energy rotational. And since energy is conserved and there's no potential energy at the bottom of the ramp, that means all this kinetic rotational will become KE linear, or nearly all of it. So when it rotates and slips, it's going faster because it is both rolling and it is slipping down. So yeah, this would be greater. Now, part 2. Indicate whether the total energy of the cylinder at the bottom of the inclined plane is greater than, less than, or equal to the kinetic energy of the previous case of rolling without slipping. So I'm going to say it is less. Because it is, when it is only rolling, the friction takes the form of KE rotational because friction causes the ball to roll. But now it's rolling and slipping, and when an object slips with friction, some of the energy gets lost as heat instead of speed because it's slipping. So some of the kinetic energy is lost to friction, so therefore the total kinetic energy will be less. The total energy in general will be less as well. And part G. The cylinder then continues to move up the other side of the ramp. Draw the force by diagram. Okay, part G. This time the cylinder is going up. Like before, there's F of G affecting the center of mass. There's FGX trying to move the cylinder downwards as it goes up. And there's F of K trying to make it go down because it is currently rolling up, and F of K opposes the cylinder's movement. Oh, this is FGY. And like before, there's Fn opposite of the surface and is equal to FGY. So, that's all the parts. I'll see you in question 3.